Imagine holding the entire internet, every movie, every book, every scientific paper in the palm of your hand, not on a hard drive, but in something far smaller, far more enduring. We're talking about DNA. This isn't science fiction, it's the cutting edge of data storage. Scientists are actively exploring how to encode vast amounts of digital information into the very building blocks of life. Could all the world's data truly fit into a single teaspoon? Our digital world is exploding with data, creating an urgent need for new storage solutions. Traditional methods like hard drives and tape libraries have limitations in terms of density and longevity. They degrade over time and require significant physical space. DNA, on the other hand, is incredibly dense. A single gram of DNA can theoretically store zettabytes of information, equivalent to billions of terabytes. It's also remarkably stable, capable of preserving data for thousands, even millions of years under the right conditions. Think about ancient mammoths or Neanderthals. Their DNA has survived for millennia. This inherent stability makes it an ideal candidate for long-term archival storage. It's a natural, self-assembling, and incredibly robust information system. At its core, DNA data storage translates the binary code of computers, zeros and ones, into the four-letter alphabet of DNA, A, T, C, and G. Specialized algorithms map digital bits to specific sequences of these nucleotide bases. For example, 00 might be A, 01 could be T, and so on. Once the digital data is converted, synthetic DNA strands are manufactured with these precise sequences. These microscopic strands are then stored, often in a dehydrated form in a small container. To retrieve the data, the DNA is rehydrated and sequenced, reading the A, T, C, G patterns. Finally, another algorithm translates these biological sequences back into the original binary code. This process effectively turns digital information into a biological molecule and back again. It's a remarkable feat of bioengineering and computer science. Significant strides have been made in DNA data storage. Researchers have successfully encoded and retrieved everything from entire books and videos to operating systems. The first full-length movie, The Wizard of Oz, was encoded into DNA. However, significant challenges remain before widespread adoption. The primary hurdles are cost, speed, and error rates. Synthesizing DNA is still an expensive and slow process, especially for large volumes of data. Reading the data, or sequencing, also takes time and can introduce errors. Scientists are actively working on improving the efficiency and reducing the cost of both synthesis and sequencing. Innovations in enzymatic synthesis and nanopore sequencing are promising avenues. These advancements could dramatically lower the barriers to entry. The potential applications of DNA data storage are vast and transformative. Imagine libraries of human knowledge stored in a space no larger than a sugar cube. It could revolutionize archival storage for governments, corporations, and scientific institutions. Personal data could be stored in a highly secure, incredibly compact format, perhaps even integrated into future bio devices. It offers a solution to the ever-growing data deluge, providing a sustainable and long-lasting method for preserving our digital heritage. While a teaspoon holding all the world's data might still be a futuristic vision, the foundational science is rapidly advancing. DNA data storage represents a paradigm shift, promising an era where information is not just digital but biological, enduring, and incredibly dense. The future of data is truly alive.